Hi guys, once again we're looking at acids and bases. This time we're going to just review the definitions of the different acids that you actually completed as a research activity in one of your other lessons. Today we want to have a look at each of the important definitions of acids and bases, and I have left Lewis' definition out of this. It's not specifically identified in the curriculum, though we will talk about Lewis structures and coordinate covalent bonds at a later stage. But for today, let's just have a look at these five important scientists, four important ideas, and what they bring. So the first one we want to look at is Lavoisier. So Lavoisier's ideas come from the 18th century, and the key thing about Lavoisier is oxygen. Now his definition focused on acids. Okay, so his definition was specifically looking at acids, and so there were a couple of interesting things that happened here. Firstly, he was focusing on the non-metallic oxides and their acidic properties. But of course, we know that things like sodium hydroxide, in fact, we know metallic oxides are basic, and they also contain oxygen, and so therefore this is a big cross as far as Lavoisier is concerned. And also something like hydrochloric acid, or muriatic acid as it was called back then, contains hydrogen and chlorine and no oxygen, and it certainly behaves like an acid. So unfortunately, Lavoisier's theory was to be replaced, and not that long afterwards, by Davy's idea about acids. Now, Davy's ideas are very much about displacement. Okay, so when you think about Davy, think about displacement, because he had noticed certain reactions in which hydrogen gas, H2, could be replaced, or more correctly displaced in solution by a metal. So if we add something like magnesium to hydrochloric acid, then what happens is the magnesium goes into the solution, it becomes an ion, and the hydrogen ions come out of the solution and they become hydrogen gas. So this observation was what led Davy to his definition of acids as being substances which contain replaceable hydrogen. He also had a definition for bases, which didn't revolve around hydrogen, but did identify that they were substances that produced salt and water, and that's our definition of neutralization reactions in general, reaction between a base and an acid to form salt and water. But this was only part of the story, and it was improved later in the same century, in the 19th century, by Svante Arrhenius. Arrhenius's idea was not just about the replaceability of hydrogen, but the fact that substances which actually produce hydrogen ions is all you need, H+ ions. And conversely, bases were ones that produced OH- ions. Now this definition's been pretty good, and it's one that we've used as I've mentioned to you before, in the junior school, because most of the solutions that you use contain hydrogen ions or hydroxide ions, depending on whether they're acids and bases, because we tend to use solutions of these, and often in the junior years quite dilute concentrations to keep you safe. So as a consequence of that, most of the contact that you would have had with acids and bases would have primarily been with ones that fulfilled the Arrhenius definition. But there were some issues with the Arrhenius definition as well, okay? Because the solvent actually had a lot to do with whether or not hydrogen ions were produced. We know rules such as like dissolves like. And so therefore, if you have something that is, hang on, I'll just write this, like dissolves like. So therefore, in water, for example, when the solvent is water, then you get a lot of these acids ionizing readily to produce hydrogen ions. But if the solvent is not water, then we have some problems with our definition of liberation of H+ ions. And of course, we also know that there are certain types of metallic oxides which may or may not liberate OH- ions, and we also know about things like sodium bicarbonate, NaHCO3, which is also a basic solution, but which does not contain hydroxide ions. So there is some limitations in the Arrhenius definition of acids and bases, and as a result, we are now going to use a better definition. The Bronsted-Lowry definition, which is almost coming up for its 100th anniversary, is one that was developed by two different scientists, Bronsted and Lowry. That's not a hyphenated name, that's two different people. And very simply, hydrogens are proton donors. The hydrogen ion is a hydrogen atom with its one proton and its one electron, where the electron has been removed. And so that just leaves us with a proton, and that's what a hydrogen ion is. And so a species that is capable of donating one of these is called an acid, a proton donor. And one that is capable of accepting one of these is a base, a proton acceptor. And this leads us to the very important concept of conjugate pairs and the ironic nature of water to be able to behave in both ways. Okay, so if we put a classic acid, so let's pick something like hydrochloric acid, which we know in aqueous solution is going to go to completion. So when we mix that with water, liquid, we are going to get a completion reaction, an H3O plus and a Cl minus, and both of these are aqueous solutions. Oops, where's that? And this is as well. So the hydrogen here has actually gone to here. Okay, so this species has donated a proton to the water molecule, and therefore the water molecule has become a hydronium ion, that's a plus. And that leaves the hydrochloric acid with a Cl minus ion, the anion, okay, an A minus, which is consistent with what we've looked at before. This species is called the acid. Oops. D, acid. And this one here is called the conjugate base. So the conjugate base is what's left when the proton disappears. And that's one of the things that's really important for us to keep in mind here, is that we have a conjugate pair between an acid and its conjugate base, or between a base and its conjugate acid. So these are the pairs, okay? These two are not a conjugate pair, all right? This is an acid, this is a base, okay? I know I'm calling water a base, but in this situation, that's the way it is behaving. It's behaving as a base. So, what happens then if we were to look at the definition of a base based on our Bronsted-Lowry definition? Well, the easiest way to do that is to actually focus on what is happening to the water molecule in the equation above. The water molecule is actually accepting a proton from the hydrochloric acid, or the HCl molecule. And what happens is it becomes the hydronium ion, which means this is now a conjugate acid. So a base conjugate acid proton pair, base conjugate acid pair, would be something like H2O and H3O plus. So the key is the H plus, okay? It's gone basically accepted in order to go from here to here. And above, if we look at the situation over here, the H2O to H3O plus, not that one, the HCl to Cl minus. What's happened here is the H plus has disappeared. It's gone. Okay, so it's gone somewhere else. So this is one conjugate pair, an acid conjugate base pair, and this is another conjugate pair. In this case, it is a base conjugate acid pair. So here's another example. and this particular species is an interesting one. It's the bicarbonate ion, the hydrogen carbonate ion. Can you identify what it's doing in this situation? Well, hopefully what you see is that the water molecule here is actually becoming a hydronium ion. So for it to become a hydronium ion, what it has to do is it has to accept a proton. So that means this must be acting as an acid, and this must be acting as a base. If this is acting as an acid, then it's going to lose its H+ ion, which is going to give to the base, and that means it's going to be a CO32- ion. So this will be the conjugate base. The water, which is acting as a base in this situation, accepts the proton and becomes the hydronium ion, which means it's going to be the conjugate acid in this situation. So here's a question from the 2014 paper. It was actually a multiple choice question where you just had to work out which of these reading straight along was the correct answer, but I think we can do better than that. I think we can actually match each of these up. So can you match each of the scientists or scientists with their particular theory about acids and bases? Well, the Lavoisier theory is the one that relates to oxygen. The proton donor is the Bronsted-Lowry one, which we've just looked at. The acids are able to produce hydrogen ions. Well, that's the Arrhenius definition. Hydrogen ions is Arrhenius definition, and Davy is the replaceable or displaceable hydrogen ions to produce hydrogen gas from a solution. So Davy is the displacement, and there's our order. Thanks for listening.